going to be really loud in the recording. So. All right, ladies and gentlemen, this class recording has started. So let me move this out of the way, and here we go. So, first, get us into section 5.3. Section 5.3 deals with friction, and friction is a force that has come up on several occasions so far, right? We encountered it first when we did our scooter acceleration lab, or we did the scooter lab, right? Friction was acting on there, you had to calculate friction. And then we calculated a couple more times when we were talking about equilibrium, especially objects moving at a constant velocity. We also encountered it in the kick disc lab that you guys did last week. We were talking about acceleration stuff, okay? So we've encountered it a little bit more, but today we want to get a little bit more into, okay, what is friction? How do we know how much friction there's going to be, et cetera, et cetera. So I start off today with the following demonstration. Ready? Here we go. No, but that's so, that's sort of the incentive to come to class, right? I mean, you can hear the demonstration, but you can't really see it. So.
Don't explain it, just push it over.
All right. So book slides across the table ultimately come into a rest. Okay? Actually, I should do that here. Let's do this to make it a little bit easier. Ready? All right. So book slides across the table ultimately coming to rest. First, there is acceleration occurring the entire time. The initial push causes a positive acceleration, but as soon as it leaves my hand, that applied force is no longer there, but the object is still moving forward, to the right in your guys' case, but eventually it comes to rest. While it's coming to rest, it's slowing down, right? Negative acceleration. And up here on the board, right, looking at these two pictures, okay, illustrating the forces that are acting on that book, although I'm missing one kind of here in the first picture, right? I should probably have a frictional force here, okay? But what do we know about the frictional force in the first picture? At least in relation to the applied force. It has to be less frictional force than applied force in order to cause the positive acceleration. But once the book leaves my hand, the applied force is no longer there, okay? But it is moving to the right still, but there's a force acting on it to the left. Is that okay? Object moves to the right, but a force acts on it to the left. Is that okay?
Yeah.
Yes, right? Right? It's causing what? Friction. It's causing net force, but net force in which direction? Well, the left, okay? Or, we kind of talked about it more generally, the opposite direction. If net force is in the opposite direction, what kind of acceleration is going to occur? Negative acceleration. Okay? Good there. That negative acceleration is what is most generally associated with frictional force. So, frictional forces resist motion. And I think that most of us are probably familiar with that idea. Okay? Down at the bottom, I don't know if we need to reiterate this, but the force that opposes the motion of one surface over another is referred to as friction. The type of frictional force that we're going to start with is what we refer to as kinetic friction. So kinetic friction acts between sliding surfaces. That term kinetic is going to show up a couple more times here, as far as the class is concerned. But kinetic means motion, right? Kinetic means moving, okay? And so again, right, kinetic friction is the frictional force encountered when surfaces slide against one another. And your book chooses to represent that with F sub K, right? F for the force, K representing the kinetic friction. Okay. Good there. The picture over on the left-hand side kind of shows us where friction comes from. We're not going to get real deep into this, but even on two surfaces like this table and that book that we consider to be smooth surfaces, okay? If you look at them down at the microscopic level or even down at the atomic level, they are not smooth surfaces. There's a lot of inconsistencies, there's a lot of jaggedness there. And, yep, if you look at it at like, like I said, a microscopic level, okay? And those inconsistencies, right, those irregularities, that jaggedness there, when those interact between the two surfaces, that's where that frictional force comes from. So even on surfaces that may appear to be very smooth, right, there's that, when you look at it down low, those inconsistencies and irregularities, especially when they interact with the inconsistencies and irregularities of the other surface, that's where that frictional force comes from. Okay? Good there. Okay. Let's talk a little bit about friction, and especially this example. So, I think most of us would probably be able to venture a guess that if I put a second book on top of this one, and I give it a push, how long will it take it to come to a stop? Less or more? Less distance, right? Okay? Now, did I push it the same, blah, 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 all those things kind of come into that play. But what we generally think of is that an object that is bigger slows down faster, right? Which is sort of consistent with Newton's second law, the inverse relationship between mass and acceleration. But remember, we kind of talked back when we talked about Newton's second law, acceleration talks about, or sorry, mass determines how much acceleration there is, but force determines if there is acceleration. And so, down at the bottom of the first page of your packet, you have figure 5.15. And unlike this example that I just did in class, they're not causing this book to slow down as it comes across the table. They're actually applying a force to it and moving it across the table at a constant velocity. That constant velocity, represented up here with the green arrow V, and in both instances, they're moving those objects with the same constant velocity. Okay? Top object is 1 brick. The bottom object is 2 bricks stacked up on top of one another. And I think that most of us would probably just sort of, logically say, okay, if I have something heavier, right, a bigger mass, but I want to move it just as fast as an object with a lighter mass, I'm going to have to push harder. Yes? I mean, logically that makes sense, okay? But when we look at it from a force standpoint, we see why that's the case. So, top picture. In order for that object to move with a constant velocity, what has to be true about the forces? They have to be the same, but they have to cancel each other out, right? An object moving at constant velocity is in equilibrium, and the net force is equal to 0. There are 4 forces in this picture, right? There's our y-axis forces, up and down. The weight of the object, and then the normal force acting on the object. And if this object is not accelerating up or down, right, those two have to be equal. Okay? And along the horizontal axis, again, 2 forces. The applied force from your hand, and then the frictional force that exists between the object and the surface that it's on. Constant velocity, right, means that those 2 forces have to be equal. Like we just said, if we're going to take a second object that has twice as much mass, in order to move it at the same constant velocity, we're going to have to pull harder. Specifically, twice as hard. Why? Because there's twice as much friction. In order to balance those two forces out, got to be the same, right? But what, working backwards, we realize twice as many bricks is twice as much gravity, so 2W, but that also means that the normal force is increased, because those two have to balance, right? Doubling the mass doubles all of those forces. Does that make sense? Okay?
Would it matter at all if the book was
No, but if we have a situation where the books do have the same mass, what we find out is that all of these forces increase by a factor of 2. Okay? They would increase, but by whatever factor that book weighs, or how much mass it has compared to the original book. Meaning, what kind of relationship are we talking about here? Proportional or a direct relationship. Okay? So, the force of friction depends on the normal force. We think of it as, oh, well, that object is heavier, therefore it's harder to move. It's kind of a domino effect in reality, though. It's heavier, so there's more weight, but if there's more weight, there's also more normal force. That normal force is what directly affects the amount of friction that is acting on that object. That direct relationship is summarized with the equation that's at the top of page 2 of your packet. And it looks like this. So, key points that we just discussed from the picture. In general, the force of kinetic friction is proportional to the normal force. That's a direct relationship. That equation that I have circled and highlighted represents that direct relationship. F sub k over on the left-hand side, N representing normal force on the right-hand side. But there's a third term in that equation. Okay? That third term is something that we refer to as the coefficient of kinetic friction. While the normal force and the frictional force are directly proportional to each other, the surface that they are on plays a role as well. The coefficient of kinetic friction tells us about the surfaces that are involved. Okay? We use a Greek letter to represent that coefficient. The Greek letter that we use is the letter mu. Okay? They gave you a little pronunciation here. Okay? We use the coefficient, or the subscript k, to represent kinetic friction. So mu sub k talks about the coefficient of kinetic friction. Okay? At least good conceptually right now. So let's talk about that coefficient a little bit more. On page 171 of your book, which you don't have, and that's fine. I'll show it to you up here. Come on. There it is. All right. Let me do... I'll just zoom in for you guys. On page 171, table 5.3, typical coefficients of friction. The very top of that table, it says rubber on concrete, rubber on dry concrete. You guys don't have this table. I didn't think it was important enough to give to you, but we'll just talk about it. So it's up here on the board for you. So, yes, sir. That's what this is about. Okay, so let me tell you what this table tells us and what it doesn't tell us. Okay, so first, the top of this table, rubber on concrete, dry concrete. Those are the tires on your car, right? it's important that there is a good amount of friction between the road and your tires. You rely on that to speed up, you rely on it to slow down, you rely on it to change directions. The frictional force that exists between your tires and the road is really what keeps your car from going in a straight line according to inertia, right? In the wintertime, when the road gets snowy and icy, right, and that frictional force is decreased, the coefficient of friction is decreased, that's when we have things like spinning out, or when you go to make that turn, you don't make that turn because there isn't enough force to change your direction. Okay? Does that make sense? So flip. Here, right, rubber on dry concrete, tires on dry road, have a coefficient of friction of 0.8, which doesn't seem very high. It's less than 1. But if you look at the list, that's one of the higher coefficients of friction. Down here, rubber on concrete wet, right? A significantly smaller coefficient of friction.
But when it snows and rains, you start with the concrete. Well, not really.
You actually, yes, because there is less friction. So now, right, friction is a force. It causes things to accelerate. The less force you have, the less acceleration you have, right? So you either try to take that turn going the same speed as you do when the concrete is dry, and you don't have enough force, so you end up going straight, inertia, right? Or you slow down so you don't have as much acceleration to do. You know what I'm saying?
Yeah.
Okay. But if we go all the way down to the bottom, right, look here, right? Steel on ice, okay? Ice skate on ice, right? Waxed skis on snow, 0.05, 0.06, significantly smaller than the coefficient of friction between tires on a road, right? We don't want friction in these circumstances. So the surfaces involved there have a much smaller coefficient of friction. Good. Well, yeah, because then concrete, asphalt, probably, I would say asphalt is probably a little bit less than concrete because the surface is a little smoother than concrete is, right? If you look at it. Yeah. I'm thinking concrete like this, like the parking lot, or like this floor, but this floor is concrete, but it's nice and polished. So the coefficient of friction here is a lot smaller than like on the road or the parking lot, right? But asphalt, asphalt is more. The parking lot is more asphalt, right? Yeah, but asphalt kind of has that. Well, depends on what you do to it. It depends on what you do to it. See, I'm thinking like you can seal asphalt, try and keep the water out of it. I don't believe our parking lot has done that, right? So
we're gonna have potholes soon.
yes. Yeah. So, but yeah, depending on what you do to the surfaces, like this floor in this room is concrete, but its coefficient of friction is much smaller because it has that coating on it, it has that sealant on it. So now, here's the point that I kind of want to make with this, okay? This table, right, when it's talking about rubber on dry concrete, or rubber on wet concrete, or an ice skate on ice, or skis on a snow, right? Skis on snow, not a snow. Okay? Notice it doesn't say anything about the object in particular that we're talking about. This coefficient of friction is the same if we're talking about a Prius versus an Escalade. This, an ice skate on ice is the same if you're talking about, a little kid who's learning how to ice skate for the first time or a professional hockey player, right? This wax skis on snow. It's the same whether you're talking about a little kid or their parent that's skiing on the same hill. The coefficient of friction doesn't tell us anything about the actual object. It's only telling us about surfaces. But I think most of us would probably figure out, right, that heavier objects, or objects that have more mass, have more friction, even though the surfaces aren't any different. Does that make sense? That's where this equation comes in. This equation tells us about the surface, that's the coefficient part, but the normal force, the N, then makes it specific to that object. Two people on skis will have the same coefficient of friction, but a person that has greater normal force, generally that means a person that has greater weight, has more friction than a lighter person. Okay? Does that make sense? So two things here, right? The coefficient of friction tells us about the surface. The force of friction tells us about a specific object on that surface. Okay? All right. So putting that to good use, let's take a look at guided example 5.11, which is at the bottom of page 2 of your packet. So, pass the salt, please. Got to be polite, even in the physics world. Okay? So it says, someone at the other end of the table asks you to pass the salt. Please. But then you're feeling quite dashing. Get it? It's like a dash of salt. Like,
I was thinking like Dasher. Yeah, that's what I was not like that.
I didn't write the book, all right? So.
Everyone watching this recording is going to hear your bad pun.
Yeah, but I didn't write the book, so it's not really my bad pun. I'm just reading. So I can't take credit for that. All right, it says, you slide a salt shaker with a mass of 50 grams in that direction. The shaker slides with an acceleration of magnitude 0.787 meters per second squared and comes to rest at the desired location, because you're that good. Right? What is the coefficient of kinetic friction between the shaker and the table? So, going back to table 5.3, right, that we were just looking at, right? Salt shaker on table doesn't show up here, right? So, it's asking us to calculate that coefficient of friction. All right. We could, I suppose, right? I don't know if salt shaker on table makes it too many lists. I don't really know. So, let's work the process. First step. What should we do first?
Write down what we're asking us.
Let's go there, right? First step in the process. What is this question asking us, right? So, what is the coefficient of kinetic friction? We use the Greek letter mu to represent the coefficient of friction. We put the subscript k on it to represent the kinetic friction. We'll change that tomorrow. All right, so we know what it's asking us for. What next? Right. Where do we go next? What we have, right? So, a couple of things that we know here, right? Okay, they gave us the mass of 50 grams, okay? Do we want our masses in grams? No, right? We want them in kilograms. So let's just change that right away. What else? Okay, gave us the acceleration. Acceleration of magnitude 0.787 meters per second squared. And I'd say there's one other piece of information that we could get out of this problem. That's more of an application of this information. There's one more thing in the problem that it tells us that may or may not be helpful, but it's a piece of information. Which velocity has? The final velocity, right? Because what does it say happens to this salt shaker? Right? So, we know that the final velocity of this salt shaker is 0. that may or may not be important, but it's information that we have to work with. Okay? All right, good there. What we're looking for, what we know, now let's go free body diagram. Okay? I know that the picture has sort of given you some forces on there, right? But let's talk about what we know, how, right? That's not actually a free body diagram in that the forces are not drawn in the right place. They're the forces, but maybe not in the right orientation. So, I'm going to draw right over this picture, okay? First thing I'm going to do, right, add some whoosh lines because that object is moving towards the right. That might be helpful to us a little bit later on. Okay? All right, so let's start adding some forces here. It's traveling to the right, so that, that's like, whoosh lines, right? Yeah. All right, so let's start adding some forces here. What's first? The weight, right? All right, we know that the weight of an object. How do we calculate the weight of an object? M times G. Okay. They gave us M, so we can figure out what that weight is. So somebody plug that into their calculator real fast. Anybody? 0.4905. All right, so this is 0.4905 newtons. Okay. All right. What else? What else? That's it? Well, let's go normal force first, okay? So, normal force in this case, right? It's going to point this way. Okay? First, we've talked about on several occasions that just because a force goes upwards, that doesn't necessarily make it a normal force. Is this a normal force? There's a surface underneath it. What do we know about that normal force? In this case, this normal force has to be equal to 0.4905. The salt shaker is moving along which axis? X-axis. Those are two y-axis forces. Is it accelerating up or down?
Nope.
It's not, so those two forces have to balance. Okay? Last force that goes on in this picture is, well, acceleration isn't a force, right? But something has to cause that acceleration, right? So, the frictional force, in this case, has to go here. Frictional force opposes motion, so it has to go in the direction opposite of the motion. And as we discussed before, with the book sliding across the table, it's okay to have the object moving in one direction, but a force pointing in the other direction. It just does what? Slows it down, which may change some of the information that we wrote down at the beginning of the problem. If we know that this salt shaker is slowing down as it slides across the table, what can we change that we wrote down earlier? The acceleration is going to be what?
Negative.
Okay, this will be a negative acceleration because it's slowing down. Okay? All right, good there. Going back to the equation that's at the top of the page that you're looking at right now. Here's the equation that relates the force of friction, the coefficient of friction, and the normal force. If we're trying to find the coefficient of friction, what are we going to have to figure out? The force of friction and the normal force, right? This equation has three terms in it. If we want to solve for one of those terms, we got to know the other two. We already know what? We already know the normal force, okay? Oop, wrong way. We know the normal force, but we have to figure out that frictional force. Even though it's negative acceleration, this object is still accelerating. And that means we can use an equation to analyze its motion. Which equation do we use to analyze the motion of an accelerating object? You should know this one. It's an important one. not the delta. Net force, right? Sigma. Sigma F equals what? M times A. What is that? I should close up my A. That whole equation is what? That whole equation summarizes what? Back like on the first day, Newton's second law, right? This equation summarizes Newton's second law, right? The relationship between force, mass, and acceleration. All right, Hans, what do we call this? Sigma. Sigma means what? The sum of all forces, not the change, that's delta, right? Okay. So, all right. How many forces do we have on this picture? There's 3 on our free body diagram, right? But what do we know about 2 of those forces? These 2 forces cancel each other out, right? Technically we have to add all 3 of them together to get the net force, but we can kind of make a jump here and go, okay, if we know we got to add all 3 of these together, but these 2 cancel each other out, that means that the only one left over is what? F of k. So that means in this case, our net force is solely the responsibility of F of k. Right? That makes our lives a little easier. And then, at the beginning, they gave us the mass, 0.05. The acceleration, negative 0.787. And so we should be able to figure out the frictional force that is acting on this object. Say again?
Negative.
935? But it's also what?
Negative.
Negative because it's going which direction?
The opposite.
Opposite direction. And it's a force, so it should have newtons on it, right? But is that the answer to our problem?
No.
It's not the answer to our problem, right? Going back here, using this equation, right, f of k is equal to mu sub k times n. If we're trying to solve for the coefficient of friction, we have to rearrange this equation, yes? Okay. And if I remember correctly, you should end up with that. Anybody actually put it through the...
I got that. I got 0.2.
Okay. All right. All right, good with that? Jason, go ahead. Because that's to be in kilograms instead of grams, right? Yeah. No, they are proportional to each other. Okay. All right.
So it's gonna be double.
So let's talk about this. Okay? So let's talk about this a little bit more. First, when you substitute in the 2 values for the kinetic friction force and the normal force, your answer comes out to be negative. Fine. However, the coefficient of friction is a scalar quantity. Okay? The coefficient doesn't have direction. It just relates surfaces. So, yes, this came out as negative when we plugged in the numbers that we got from the problem, but that really doesn't mean anything, at least in terms of our problem. Okay? So, I'm just going to get rid of it. If you leave it on the test, I won't mark it wrong, because that's what you get when you do the calculation. Okay? Second, I will mark this wrong, however. In order to get the coefficient of friction, you had to divide the normal force the frictional force by the normal force. Unit on frictional force. Newton. Unit on normal force. Newton. If you have newtons over newtons, what happens? Well, they cancel each other, meaning that the coefficient of friction is a unitless quantity. Okay? It is not a measurement. It is a ratio between the two surfaces. It's a characteristic of the surface. It's not an actual measurement of anything. Okay? It compares two things to each other, and therefore it does not have a unit. Okay? Good there.
Yep.
I want to do one more thing. Down at the bottom of page 2. Down at the bottom of page 2, right underneath the problem that we just did, it says, follow up. Suppose the coefficient of friction is equal to 0.12. What is the acceleration of the salt shaker? So, let me go back here, right? You don't have to write anything down. You don't have to answer anything. Just let me talk. Here, is the equation that relates force of friction to normal force to the coefficient of friction. We calculated that the coefficient of friction between the salt shaker and the table is 0.08. In the follow-up question, it wants to make it 0.12. So let's say we're replacing the smooth table that the salt shaker is sliding across with like a tablecloth. Right? That changes the surface. That changes the coefficient of friction. However, changing the surface, does that do anything to the normal force? The normal force, we haven't changed the salt shaker at all. Just by putting a tablecloth underneath it, that doesn't change how hard gravity's pulling on it, and that doesn't change the normal force. So, N will remain the same, but the coefficient has increased. If the normal force remains the same and the coefficient increases, what does that do to the force of kinetic friction? There is more kinetic friction force. If there's more kinetic friction force, what does that do to the acceleration? More force means more acceleration. But remember, what kind of acceleration are we talking about here? Negative. If you have a greater negative acceleration, what's going to happen to that salt shaker?
It slows down faster.
Slows down faster. Will it make it all the way across the table to the person that you're trying to slide the salt to?
Probably not.
Probably not. Okay? So increasing the coefficient of friction doesn't necessarily do anything to the object itself, but it will increase the frictional force because of the change in the surface. Okay? So from a conceptual standpoint, right, even though we didn't actually work out the problem, from a conceptual standpoint, if we change the coefficient of friction to 0.12, the acceleration of the salt shaker will be increased, but still negative, meaning that it will slow down faster or slow down more quickly, and therefore it won't make it all the way to the end of the table where you want it to go. Not off the top of my head, but
Can you put it on the board
hold on a second. $31, is that what the number was? Yeah. So all right, it's good there. So, for tonight's little bit of homework. about friction in general. Okay. So a couple of problems. Most of them are conceptual problems. I think there's one short calculation, but most of it is conceptual. So a little bit at the end of 5.3, and then some at the end of chapter 5. Okay. Tomorrow we'll talk about static friction, some similarities, but also some differences.
I'm excited.